In this screencast, we're going to talk about intermolecular forces and how they influence properties of organic molecules. And some of this will be a review from general chemistry. So I want you to remember that intermolecular forces are, and I'm going to abbreviate intermolecular forces as IMF, are interactions between molecules. So, for example, I want you to look at HCl, right? And we have a strong intramolecular attraction, which is a covalent bond between the hydrogen and the chlorine. But we have weak intermolecular attractions between the two molecules of hydrochloric acid. And so what we're focusing on here are the interactions between molecules. Now, functional groups determine the type and strength of these interactions. Now, ionic and covalent molecules have very different intermolecular forces, and we're going to look at both of those. So let's talk about ion-ion interactions. So ionic compounds contain oppositely charged particles. Right? And so those are held together by extremely strong electrostatic interactions. Right. So these ionic interactions are much stronger than the intermolecular forces present between covalent molecules. Right? And so an example of that, sodium chloride, and you can see, we have the chlorine ions that are negatively charged with the sodium that are positively charged. Now, when we talk about intermolecular forces in covalent molecules, there are kind of three big forces that we're going to talk about, and they increase in strength. The first one is van der Waals forces. Right? The second is dipole interactions. And then the third is hydrogen bonding. So van der Waals is the weakest, hydrogen bonding is the strongest. Let's talk about van der Waals forces. Now, van der Waals forces is a little tricky because it has a lot of names. It's also known as London forces or London dispersion forces or just dispersion forces or induced dipole interactions. Okay, so these are just weak, very weak interactions caused by momentary changes in electron density in a molecule. Right? Now, what do I mean by this? Okay, so I want us to look at two atoms. These are helium, okay? But this would be the same thing sort of in methane. So we've got helium here, and we've got electrons that are dispersed, and all of a sudden those electrons run over to one side. And what this does is it causes this to be partially negative, so this side. Well, negatives repel each other, so these electrons say, no, I don't want to be over here, I want to run to the other side. So when they run to the other side, now this side of the molecule right here is partially positive. And so this molecule has induced a dipole into this molecule, and that's why we call it induced dipole, twice forces. Now, you have experienced these forces if you have ever taken out any cling wrap or saran wrap. When you pull it out of the box, there's a momentary disturbance of the electron cloud with the hydrocarbon. So that's just a large sheet of carbons and hydrogens. And what happens is with the static electricity, all those electrons run to one side and it induces an attraction, and that's why your cling wrap bubbles up, right? And it's hard to stretch over things. Now, this is the only attractive force in nonpolar molecules. Okay, so that's something to keep in mind. All compounds, though, do exhibit van der Waals forces. The larger the surface area of the molecule, right? The larger the attractive force between the two molecules. Right? And that means it's a stronger intermolecular force. Now, let's talk about what I mean by surface area here. I want you to look at, this is pentane, which is a straight chain molecule, right? And so it's 1, 2, 3, 5 there. And then this is neopentane. Now, neopentane is a smaller molecule. Looks like this. And so what happens is if you have a linear molecule like this, these guys can line up and get really close to each other, and they have a lot of intermolecular forces. When you have neopentane like this, it's more spherical, and so when it encounters another molecule, there's not as much interaction, so there isn't as much intermolecular forces. As the strength of the intermolecular forces increases, you are going to see the boiling point increase. And so the reason this is because you can kind of think about these as a glue, where in the liquid phase, these intermolecular forces act as a glue and hold those molecules in the liquid phase. And you have to have enough energy or to pull those molecules apart and fling them into the gas phase. And so what you see here is that the boiling point of normal pentane is 309.4, but neopentane is 282.7. And so that shows us that there are less intermolecular forces here in these spherical molecules. I like to call this my spaghetti and meatball theorem because linear molecules kind of look like spaghetti noodles, and when you make spaghetti, those spaghetti noodles stick together, and then the spherical molecules look like meatballs, and it's a lot easier to separate meatballs. So if that works for you, that's great. If not, just you can ignore that. The other thing that we see is that large atoms, right, also have stronger intermolecular forces than small atoms. So large atoms have stronger intermolecular forces than small atoms. And so look at these boiling points here. These are organized by period, so 2, 3, 4, and 5. And you can see neon, argon, krypton, and xenon shown here, as well as our halogens, fluorine, chlorine, bromine, and iodine. All of these just have van der Waals forces, and we see as the size and molecular weight increases, the boiling point increases, indicating that those molecules are being kind of, there's more attraction between those molecules holding them in the liquid phase. So one of the reasons for this is because of polarizability. Right? And polarizability is a measure of how the electron cloud around an atom responds to changes in its electronic environment. Right? And so larger atoms have more loosely held valence electrons, right? And so they're more polarizable than smaller atoms. Right? Okay, so van der Waals forces, right? We see they increase with size and then they increase with surface area. And all molecules have them, and they're the weakest intermolecular force. They're the only intermolecular force that hydrocarbons have, okay? But we don't just have hydrocarbons in organic chemistry. We also have functional groups with heteroatoms. And so those molecules can have dipole-dipole interactions. So dipole-dipole interactions are just the attractive forces between the permanent dipole of two polar molecules. Right? So let's look at acetone. Acetone has oxygen here. It's very electronegative, so it's partially negative, and then that makes that carbon partially positive. And so this is a polar molecule. What happens is these partial negatives and partial positives will attract each other and cause there to be intermolecular forces between the molecules, right? So visualize this like glue. They're kind of holding them together. But kind of like, like if van der Waals was like the glue that holds a sticky note on, this would be like rubber cement, right? Where it's kind of easier to pull apart the van der Waals. It's a little harder to pull apart the rubber cement because it's, or like a glue stick, right? Because it's just a little bit more than what you would see on a sticky note, okay? So when we talk about this, these are stronger than van der Waals forces. Now, there's a special type of dipole-dipole interactions that's even stronger, and that's hydrogen bonding. So hydrogen bonding generally occurs when you have a hydrogen atom bonded to a fluorine, oxygen, or nitrogen atom, right? That is electrostatically attracted to a lone pair of electrons on an oxygen, nitrogen, or fluorine atom of another molecule. All right, and hydrogen bonding is the strongest of the three types. An easy way to remember this is it's kind of like fun, but not quite. It's FON, fluorine, oxygen, and nitrogen. And we show hydrogen bonds with these little dashed lines here. So, for example, oxygen has a lone pair of electrons here, and it can form a hydrogen bond with the hydrogen of another oxygen atom, of another water molecule. Here, I said oxygen atom, that's not what I meant. I meant water molecule. Here with the hydrogen atom. And so you can see there's an intermolecular force here. We can also visualize it using the electrostatic maps as well. Now, here is a summary of the intermolecular forces that we've talked about. Here's the type of forces, here's their relative strength, who tends to have these forces, and examples. Now, I want you to understand something. For example, I want us to look at water. And if we were to list all the intermolecular forces, for water, this is additive. Water has hydrogen bonding. Which means it also experiences that dipole-dipole, because you can't have hydrogen bonding without dipole-dipole. And it also experiences van der Waals, because everything experiences van der Waals. So that's something to understand, is that these are additive. The other thing is, as the polarity of an organic molecule increases, so does the strength of the intermolecular force. Okay, so we'll see that particularly with our dipole molecules. Let's talk about how these affect the physical properties. So the boiling point of a compound is the temperature where a liquid is converted to a gas. And so when you're boiling, energy is needed to overcome those attractive forces in the more ordered liquid state. Okay, and so that means for us, the stronger the intermolecular force, the higher the boiling point. So that means compounds with van der Waals forces will have a lower boiling point, then dipole-dipole, then hydrogen bonding. So let's look at some examples. We have pentane, butanal, and butane-1-ol. We've got a hydrocarbon here. It just has London or van der Waals forces. Then we have butanal, and this molecule has dipole-dipole interactions. It does not have, while it does have an oxygen, if it's all by itself, it does not have, there's not another compound that has a hydrogen attached to an oxygen. So it does not have any hydrogen bonding. And then we have butane-1-ol here, which will have hydrogen bonding. And so that has the highest boiling point. Now, other factors affect boiling point as well. as you can imagine, surface area does. So boiling point increases as the surface area increases. And the polarizability of the atoms increase. So maybe you're like, great, we see where boiling point increases. What happens with melting point? And that's a great question. So melting point is just the temperature where a solid is converted to the liquid phase. And in melting, energy is needed to overcome the attractive forces in the more ordered crystalline solid. So the stronger the intermolecular force, the higher the melting point. So that trend is the same as the boiling point. Now, given the same functional group, the more symmetrical the compound, the higher the melting point, right? So for covalent compounds or molecules of about the same molecular weight, the melting point is really going to depend on the functional group, right? So the stronger the intermolecular attraction, the higher the melting point. So let's talk about symmetry there. So for compounds that have that same functional group and similar molecular weights, the more compact and symmetrical the shape, the higher the boiling point. And so maybe you're curious as to why this is. Well, a compact symmetrical molecule like, for example, that neopentane, which is here. This is neopentane, right? Packs well into a crystal lattice. Right? Whereas isopentane here does not, right? So when you have symmetry and you're compact, you're more likely to pack well into a crystal lattice of a solid, right? And so what we see then is that neopentane has a much higher melting point than isopentane does, okay? Now, let's talk about solubility. When we talk about solubility, solubility is just the extent to which a compound which I just want to refresh your memory, which can also be called a solute, dissolves in a liquid which of course we call the solvent. And so I have an example for you here. Here's your solute, there's your solvent. And what's happening here is there are interactions between the solute particles. And so energy is needed to break up the interactions between the solute, right? And that comes from the new interactions between the solute and the solvent. So here are new solute-solvent interactions. So compounds dissolve in solvents having similar kinds of intermolecular forces, right? Likes, dissolve, likes. And so you've heard that before, probably. And so what does that mean? That means that polar compounds dissolve in polar solvents, and nonpolar compounds dissolve in nonpolar solvents. All right. I want to bring up a few nonpolar solvents that we see pretty frequently in organic chemistry. One is hexane, okay, which is C6H14. And then we also see carbon tetrachloride, which is CCl4. Okay, so those are some of our common nonpolar solvents. Weakly polar compounds will also dissolve in nonpolar solvents. So for example, your book says nonpolar compounds or weakly polar compounds. Okay. So let's look at solubility in ionic compounds first. Most ionic compounds are soluble in water. But insoluble in organic solvents. So to dissolve an ionic compound, and we've got an image of that here, the strong ion-ion interactions between the cation and the anion in the ionic compound need to be replaced by weaker ion-dipole interactions. Now, I want to remind you, ion-dipole is exactly what it sounds like. It's an interaction between something that is an ion, right? So we're going to have a positive or negative charge or something that's ionic and a polar compound. And so that's that interaction we're going to see. Now, an organic compound is water soluble only if it contains a polar functional group capable of hydrogen bonding with the solvent for every 5 carbon atoms it contains. So let's put some words to that. An organic compound is water soluble only if it contains one polar functional group capable of hydrogen bonding with the solvent for every 5 carbon atoms. All right. So for example, compare the solubility of butane and acetone here, right? And we're looking at the solubility in carbon tetrachloride, which is an organic solvent, right? Which we say is a lot of times non-polar, right? And sorry, I put those quotes in the wrong place. Organic solvent, it's non-polar. And so we see butane here is soluble in CCl4, right, carbon tetrachloride, but it's insoluble in water. However, acetone, because it has these this carbonyl functional group, that and only 3 carbons to 1 oxygen, right? 1, 2, 3 to the 1 oxygen here. Then we see where it can be soluble in both carbon tetrachloride and water, because the oxygen atom can hydrogen bond with the hydrogen atom of the water. Okay. Now, the size of the organic molecule with a polar functional group determines its water solubility. So let me put that down. The size of an organic molecule right? So a low molecular weight alcohol like ethanol, shown here, is water soluble. But cholesterol, which is huge, right? It's got 27 carbon atoms and only 1 OH group, has a carbon skeleton that's really too large for the OH group to be solubilized by water, okay? So that means cholesterol is insoluble in water, okay? The nonpolar part of the molecule that's not attracted to H2O is said to be hydrophobic, and the polar part of the molecule that can be attracted to water is said to be hydrophilic. So, for example, in cholesterol, the OH here, that hydroxyl group, that's hydrophilic, while all of these carbon and hydrogen all these carbon and hydrogen atoms, the skeleton is said to be hydrophobic. So I just kind of want to end with a table of that summarizes the solubility. You can see here we have ionic compounds. They're soluble in water, insoluble in organic solvents like carbon tetrachloride or hexane. Then when we talk about covalent molecules, and we have butane here, it's insoluble, and that means it's insoluble because there's no nitrogen or oxygen atom present to hydrogen bond to water, but it's soluble in organic solvents. But once you have an alcohol group present, then you can be soluble in water as long as you have less than or equal to 1 oxygen atom for every 5 carbons. Okay. And then, so this here, there's 1 oxygen atom for 11 carbons, and so that's too large to be soluble. So that would be an example of another molecule that's insoluble in water, like cholesterol. So this ends our screencast of intermolecular forces and properties of organic molecules. If you have any questions, please feel free to stop by my office.